Yeah, so I'm actually not constrained to talk about FRBs or even astronomy. Unfortunately, I don't have any expertise outside of astronomy. I barely have any expertise outside of FRBs. So I'll stick to those two things. Actually, maybe I'll go a step further and say I don't even have expertise in the sort of subfield of FRBs that I'll be talking about today, because these are all fairly speculative ideas. Okay, so Ido mentioned yesterday this sort of bifurcation of efforts, where all relevant FRB questions kind of fall into these two broad silos at this point. What are FRBs and what are they for? In the former category, we have all of the stuff we've been talking about this week. The title of the workshop is the Astrophysics of FRBs. So, emission mechanism, what is the origin of the periodicity, what is the statistics and prevalence of repetition, what are the host galaxies like, and what are the local environments like within the host galaxies. In the latter category of how can we use FRBs, how can we use them as a probe, there have been a lot of really nice theoretical ideas ranging from cosmology, which we'll hear about next, to sort of fundamental physics, gravitational lensing, as well as baryon studies, trying to probe the free electrons and the CGM, IGM of intervening galaxies. And we've sort of emerged recently from this era of those papers being purely theoretical and forecasting to actually applying these sorts of FRB applications, like in Xavier's paper from last year. So I'll talk today about a couple of these things and how, depending on what your science goal is, depending on what you're trying to learn about FRBs or how you're trying to use them, you can end up actually requiring fairly orthogonal survey setups and instrument designs. And so I'll talk a little bit about how you can maybe reach a compromise and optimize the amount of science you want to get out of a given survey. So for FRB gravitational lensing, I know a few of you have thought about this already. If you haven't, the basic idea is we have some FRB at maybe a gigaparsec or something, and as it travels to us, it gets lensed by an intervening compact mass, and then we end up seeing two copies of the FRB with our telescope. And in principle, we should have voltage data saved for this FRB, which means we should be able to, under certain conditions, we should be able to correlate that time stream after removing dispersion, after removing channelization, correlate that time stream with itself, and find a peak at a non-zero lag. So this is how you sort of differentiate between just a repeating FRB in the same direction and an actual gravitationally lensed copy. Now, the thing that is special about fast radio bursts is, first of all, they're very narrow. They're about a millisecond in duration. So if you have a lensed copy of that FRB, you know the lensing delay to a millisecond. But you can actually do better than that because you have baseband data. You have roughly the sampling time of the telescope. So you can get lensing delays down to tens of nanoseconds. Okay, and of course, you also have all the way up to the duration of the survey, which could be several years, corresponding to massive galaxy lenses or even clusters. So this figure shows delta t and delta theta as a function of the lens mass. So delta t, this is the lensing delay, and it scales as the lensing mass. This is the angular separation in the sky of the two images, the two lensed images, as a function of lensing mass, and it scales as the square root of the intervening mass, and this just comes from Fermat's principle. And the amazing thing about FRBs is that you end up with access to like 17 orders of magnitude in lens masses because you can access these nano-lensing events, because you have baseband data. And you can also go all the way up to these sort of 3-year lensing events. Now, a lot of work needs to be done on how to actually do this algorithmically and how to design your surveys such that you guarantee that you'll see the second lens copy show up. But nonetheless, in principle, you can go from sort of 10 to the 4, 10 to the minus 4, 10 to the minus 5 solar masses up to 10 to the 12 solar masses in lensing mass. Okay, and people play this game with AGN. So lens quasars have been used for this technique called time delay cosmography, where because this distance here is proportional to 1 over h naught, you can actually try to constrain the Hubble constant based on these time delays if you have a cosmological lensing event. You also need to know the the mass profile of the lens, which can be quite tricky. And this is where FRBs can be fairly useful. Because you have this flash for 1 millisecond, and then when the lens event shows up, it's also just a flash for 1 millisecond. You can remove the background. You can just subtract the difference, and you don't have to worry about some of the substructure that can get in the way. This has been discussed in a paper by Zittrain and Eichler, where they talked about trying to do so-called real-time cosmology with a repeating strongly lensed event. And I include the abstract here because it starts with the best sentence of any abstract of 2018. It says, "It's noted that the duration of an FRB is a smaller fraction of the time delay between multiple images than the human lifetime is the age of the universe." And on it goes about how you can actually watch the universe expand in real time if you have a repeating strongly lensed FRB. So when this came up on Monday, we talked about how this is going to be difficult with a transit instrument. If the typical time delay for a massive galaxy lens is sort of days to weeks to months, with an instrument like CHIME, you have to get very lucky. You have to land on the exact same source when that lens copy shows up. And there's no guarantee of that. One way to get around this, though, is to observe one of the celestial poles. So if you put, say, your 50 square degree field of view on the NCP at all times, then you know that you're always observing the same patch of the sky. You're not going to miss the lens copy of the event. And this is also good for trying to understand FRB repetition statistics and looking for periodicity too. Because you're going to catch every repeat burst from a given FRB, even if it's not lensed. Another interesting thing, another interesting scale that one can access, and Harish mentioned this today, is a sort of dark matter subhalo size lenses, which might be 10 to the 6 or 10 to the 9 solar masses. And these are hard to go after if you're trying to study strongly gravitationally lens events just with imaging data, because at this point you're at sort of tens of milliarc seconds. Whereas for an FRB, the time delay might be 100 seconds or 300 seconds, which is well within the transit time of a transit telescope like CHIME. And it's kind of interesting. So people try to understand the nature of dark matter and its clumpiness by looking at these substructures in strongly lensed optical galaxies. But it turns out if you go to high enough redshift, then the lensing probability, this sort of optical depth, is actually dominated by field halos. And so one could look at all the CHIME FRBs for which baseband data was dumped, look for these sort of 100-second or 200-second time delays, and if you don't see anything, then you could potentially constrain how many dark matter subhalos there are floating around at 10 to the 8 solar masses. And then Harish also mentioned this, but microlensing is a really exciting prospect for fast radio bursts. And this is, again, because you have such high time resolution data and you preserve phase information, you can actually look for gravitational time delays that are shorter than the duration of the pulse. So in this way, you can go after machos, in which some fraction of dark matter may still reside. You can go after stars. Lensing event from a Jupiter-sized object could be 10 nanoseconds or 100 nanoseconds or something. So this just gives you an idea in the sort of checker of the range of scales you can access with a 3-year VLBI survey that saves voltage data. For example, Puma or Chord or DSA 2000. So this is what we actually need if we want to achieve any of this. We need voltage data for lots and lots of FRBs, maybe thousands, tens of thousands, or even 100,000. Ideally, you'll have VLBI, such that you can actually spatially resolve for the really strong lensing events. We're probably going to need new algorithmics. We need to remove the dispersion very precisely. We also need to inverse PFB the data if it's been channelized. And we need lots of high redshift events, which means we can't keep missing these really high DM events due to interchannel dispersion smearing. We have to make sure that we actually have access to really distant FRBs. And this just shows you why. This shows you the rate less than some Z max of strongly lensed events, and you can see that there's this volume term. So you need to go out to high Z max, and you can see that this probability of strong lensing increases very rapidly until you get to redshift 2 or 3. One thing I thought of yesterday after Ryan's comments, Ryan made a comment in a discussion section on Monday about how if you had a strongly lensed event, then it would be hard to tell the difference. It would be hard to know that you weren't just looking at two different FRBs because they would have substantially different dispersion measures. If you had a VLBI survey and you could resolve with milli-arc-second resolution, then you actually could know that it was a lensed event, even if they had dispersion measures differing by 10 or 100 units. And this would be a really clean probe of the CGM of that intervening lensing event, lensing galaxy, right? So unlike the sort of situation that Brian talked about yesterday where you have two nearby FRBs in the sky, in this case, the three images have the exact same localhost DM, they've got the exact same IGM DM, they've got the same Milky Way DM, so the only difference in the observed DM is going to be the halo from this lensing galaxy. So we at Aperitif, we put out a paper this morning where we intersected the halo of a intervening galaxy. Unfortunately, we only had one image of it because the geometry wasn't favorable for lensing. This is it. It's very bright. It comes within 18 kiloparsecs of local group galaxy M33, which means it also skewers the sort of M31 halo, which is much larger and in which M33 resides. So this is a figure from modeling done by Xavier last year. You can see M33 has this great big CGM, or M31 does rather, and M33 lives in it. So unfortunately, we don't detect any significant scattering or scintillation from this halo. It probably just adds some, maybe 10% of the dispersion measure. We wondered whether or not the relatively large RM of 500 might be caused by M33's halo, but we couldn't find any evidence of that. So probably it just lives in a relatively dense magnetoionic environment in the host galaxy, like a star-forming region. One nice thing about carrying out an FRB survey on Aperitif is that before we knew much about FRBs, Aperitif was an imaging survey, and so we already had a radio image, continuum image of this field. We didn't see any persistent radio source there. This is a slide, so switching gears a little bit, this is a slide that a few of you have already seen before, I think. And here I'm asking, might we run out of FRBs? The idea is as follows. So suppose there are 1,000 bursts across the sky each day. Suppose that on average they repeat with a frequency of once per week. Well, then there's only actually 7,000 FRBs in the observable universe that you have access to. And that means also that there's only 7,000 galaxies in the observable universe that host an FRB. So the Milky Way is almost guaranteed to not have an FRB like the ones we've been seeing, if repetition is fairly common. But what this also means is the fraction of events that a survey like CHIME sees over time that has already been seen to repeat approaches 1 asymptotically. Now, this is a cartoonish example. We know that the FRBs that do repeat seem to do it much more regularly than once per week. And it's probably the case that the ones that there are lots of FRBs that repeat less regularly than that. But nonetheless, the shape of this curve, f as a function of time, its first and second derivatives can tell you something about the distribution of repetition rates. So this will be interesting to watch as CHIME detects FRBs for the next few years. Now, it's a little bit misleading phrasing it like this, running out of FRBs. What this really means is you might exhaust the FRBs that your particular survey setup has access to. So this means the volume out to which you can search, the fairly narrow and limited time range that you're sensitive to in terms of widths, and modulated, of course, by the DM selection function that you have. So you can just change the parameters of your surveys, maybe swap beams for time resolution, maybe swap time resolution for frequency resolution and go after higher DM events, and now you have more FRBs and you've no longer run out of them. Okay, I've got about 10 seconds left. So just to wrap up, I want to emphasize that different science goals are going to require fairly different survey strategy. So I think there was some consensus yesterday and the day before that if we really want to understand the host environments and maybe even the emission mechanism of fast radio bursts, we need one that's fairly nearby. So how do you find an FRB that's 20 megaparsecs away? Well, it would be helpful to know something about the luminosity function, because if the luminosity function is relatively steep, if it's steeper than the Euclidean value, then FRBs tend to be quite nearby. And we can go out with a really large field of view, low sensitivity survey and try to find those nearby FRBs that way. If we want to target high DM events, well, then you need to make sure you're not too affected by interchannel dispersion smearing, which means, again, you might want to crank up the number of frequency channels that you have and give up some time resolution such that you can go for DM 5000 events. Similarly, if you're looking for something that only has a DM of 80, a nearby event, then you might want to crank up the time resolution, give away some frequency channels, and then you can look for these very narrow FRBs that almost certainly exist, which are tens or hundreds of microseconds in duration. Yeah, so actually I'm out of time, so I'll leave it at that. Thanks.